So this is today. So we have already seen neural networks and deep learning, improving deep neural networks, structuring machine learning projects. So today we will see convolutional neural networks, and this is the fourth course of the deep learning specialization at Coursera, which is moderated by deeplearning.ai, and the course is taught by, officially taught by Andrew Ng, which is what we are following. And so this, by the end of this class, you should be able to understand how to build a neural network, including the reset variations such as residual networks, to know how to apply convolution neural networks to object detection, or which is also known as visual detection and recognition tasks. And also, you should know how to, you would be able to know how to use neural style transfer to generate art. And you can apply these algorithms to a variety of image, video, and that is 2D or 3D datasets. So we'll first discuss some basics of computer vision, because convolution neural networks are applied to the computer vision problems. And yeah, so it's computer vision is one of the application, uh, so which has rapidly advanced due to deep learning. And some of the applications of computer vision include self-driving cars, face recognition, and so you would be seeing on a daily basis in your mobile phones. The So these days the latest cameras, they can create a square over your face. They can tell whether what is the age of the live. That's known as online, that's known as online prediction. So and you can so deep learning is also enabling lots of new types of art. So there is a website. Okay, so yeah, I think this one, neural style dot art, or yeah, this one, deepart.io. So in deepart.io, you can basically choose your image, you can choose a style, and you can basically combine these two images and become a digital artist. So with the style as the image too, you can basically apply this style to this image. So you can just try it live. So you can uh, either this so they have so popular style. So you have to drag your photo. You just drag your photo here, or they say that okay, so pick it from the computer, and then you can choose a particular style. You put your email address here, accept the policy, and they will basically mail you the artistic image. So you can see people have created. So for example, this image plus this style results in this neural art, which is powered by deep learning, and we can use this technology. So this is based on generative adversarial networks, which are also a form of convolution neural networks, and we can use this for our climate science and applications which are scientific in nature. So that is about art. So deep learning is enabling new types of art. Anybody can become an artist these days. So also rapid changes to, yeah. So people are making new different applications which were not possible a few years ago. And computer vision, deep learning techniques are always evolving. So people are coming up with new architectures. and which can help us in other areas other than computer vision. So, as we were talking about, our application is climate science. So, for example, Andrew took some ideas from computer vision and applied to speech recognition. Other things that can be done is our image classification. So, as we have also discussed before, you can classify different objects from the satellite imagery. You can classify different weather events. You can based on your project, you can do image classification. Now, a step ahead of image classification is object detection. So you are basically actually uh, exactly detecting where in the image the objects are. So you have to also, rather than just saying that whether this image has a cat or a dog, you have to tell at what location, and you have to draw a box over the classified object. So you have to basically detect the object and localize them. And then there is neural style transfer. So you can change the style of an image using another image. Now, so one of the challenges is for computer vision is that the images can be large, and we want fast and accurate algorithms to work with them. So, for example, a 1,000 by 1,000 image will represent 3 million features or inputs to the fully connected neural network. In the If the following hidden layer contains 1,000, then we would want to learn weights of the shape 1,000 comma 3 million, which is around 3 billion parameters, and becomes computationally very expensive. So one of the solutions, so this is what so this is when you are not using convolution neural networks. So this is when you are basically, so what we were doing in our examples of MNIST data, we were having a data set of size 28 by 28, and we were basically flattening out that into a 1D vector of size 784 by 1. So that's what he's saying, that if you are having a 1,000 by 1,000 image, so and with 3 million features or inputs, so that basically, and so you will have to use a lot of parameters, and to avoid that, and also to basically preserve the spatial patterns in the data, we go for convolution neural networks. So in a convolution, what basically happens is you have a convolution operation, which is the fundamental blocks of a convolution neural network, which is also the CNN is the short form of convolution neural network. And one of the examples is image. Okay, so and this is your weight, or this is your filter, we can say. So the filter is identifying vertical edges. So you have 1 1 1 0 0 0 and -1 -1 -1. You would apply a convolution on this. So you would basically, we would apply convolution and on this matrix, and you would use some stride. So you would move this filter over this 2D matrix. And so convolution is basically, so you would say, if you are putting this filter over this part, so you would say 1 into 1 plus 7 into 0 plus 8 into -1 plus 6 into 1 plus 2 into 0 plus 8 into -1 plus 2 into 1 plus 3 into 0 plus 9 into -1. So that comes out to 16. And so early layers of CNN might detect edges, and then the middle layers will detect parts of objects, and the later layers will put these parts together to produce an output. Now, in an image, we can detect vertical edges, horizontal edges, or you can do a complete detection. And this is what he's saying is a example of a identifying or detecting vertical edges. So you can see that the size of the output after convolution, it decreases. So this is a matrix of size 6 by 6, and you are applying a convolution filter of 3 by 3 with a stride of 1. So 6 minus 3 plus 1, so that becomes 4 by 4. And yeah, so if you want to make the convolution operation in TensorFlow, you will find the function TF. So TF is you have imported TensorFlow as TF dot NN. So there is this neural network library in TensorFlow, and then we have this con2D class. So in Keras, you will find the con2D function. So with a C capital, and here you can see that this so this con2D from TensorFlow has starts with a small c, and so this con2D function would typically use this con2D from con2D from Keras will use the con2D from TensorFlow. And the vertical edge detection will filter will find a 3 by 3 place in an image where there are bright regions followed by dark regions. So basically this filter will try to identify. So you can see that this 111 is a bright region, and then it's followed by a dark region. So what this filter is trying to do is it's something like the filters that people use in digital signal processing. So you are trying to identify places where bright regions are followed by dark regions. So the gradients from bright to dark. And if we apply this filter to a white region followed by a dark region, it should find the edges in between the two colors as positive values. But if we apply the same filter to a dark region by followed by a white region, it will give us negative value. So to solve this, we can use the absolute function to make it positive. Now to detect the horizontal edge, you would use a filter which is something like this. So you would have the numbers 1 in the rows, and then zeros in the second row, and then -1 in the third row. And there are a lot of ways you can make we can put the number inside the horizontal or to 1. And then there is something known as sharp filter. So the idea is taking great care of the middle row. So that is 3, 10, 3, 0, 0, 0, minus 3, minus 10, 3. And we have learned that in deep learning, we don't need to handcraft the features. We can treat them as weights and then learn these weights. So these are this is the weight matrix, and you can basically so you can apply these weights or these filters, and then you can learn these values from the data, and they can learn horizontal, vertical, angled, or any type of edge automatically rather than getting them by hand. Now there is this concept of padding. So in order to use deep neural networks, we need to use paddings. So we saw in this last section we had a 6 by 6 matrix, and 3 by 3 kernel was, or the filter was applied to this 6 by 6 matrix, and a 4 by 4 output is generated. So you can see that we saw 6 by 6 matrix convolved with a 3 by 3 filter. It gives us a 4 by 4 matrix. And to give it a general rule, if a matrix n by n is convolved with f by f filter, it gives us n minus f plus 1 by n minus f plus 1 matrix. And the convolution operation shrinks the matrix if f is greater than 1. So so if this number f, so if you are using a filter of size 1, so you can see you will convolve over each number. So that is basically just multiplying that particular filter, which becomes a scalar. So then the matrix size remains the same. Otherwise, if it is f is greater than 1, then the size of the matrix output matrix decreases. And we want to apply convolution operation multiple times. But if the image shrinks, we will use a lot of data in this process. And also the edge pixels are used less than the other pixels in the image. So the problems with the convolution are that it shrinks the output and it throws away a lot of information in the edges. Now for our problems, for example, this is a part of a data over the globe. We won't have the edge problem, right? We would basically extract, our data is not having any discontinuity, so we can just extract the boundary values or the edge values from the neighboring pixels. So, but for image type of problems, the convolution would shrink the output, and it would throw away a lot of information that are in the edges. Now, to solve this, we can use padding. So, padding is basically you fill the you create you create something like ghost nodes, which are outside of this 2D matrix, and you just fill them with zeros. So you can pad the input image before convolution by by adding some rows and columns to it, and we call that the padding amount p, which is so the number of rows and columns that we will insert in the top, bottom, left, and right of the image. So you can pad with one row, you can pad with two, so that is the padding value p. If you are padding with one, then a uh, single rows and columns of zeros would be added. So otherwise, if this is two, then two rows or columns would be added. And in most of the cases, almost all the cases, so the padding values are zeros. And the general rule now is that if a matrix n by n is convolved with f by f filter and a padding p with a padding p, it gives us a matrix of size n plus 2p minus f plus 1. So that is the output it gives. So if padding is 1, so you can see from here. So if padding is 1 here, okay, and so this gives us n plus 2 minus f plus 1. So this is n minus f plus plus 1, that would eventually give us that. And if n is 6, size of the filter is 3, p is 1, the output will be 6 plus 2 into 1, which is 2, minus 3 plus 1, so we get 6. So we maintain the size of the image. And same convolutions, some same convolution is a convolution with a pad, so that the output size is the same as the input size. So how to find out the padding such that your output size is equal to the input. So you just do size of the filter minus 1. So in this case, 3 minus 1 divided by 2. So that gives you 3 minus 1, 2 divided by 2. So padding is 1. And in computer vision, f is usually odd. So the filter size is that is chosen is generally odd. And so some of the so it you would basically get an integer value of p. Now there is something known as strided convolution. So you can also, while convolving the filter along this 2D matrix, you would basically take steps of one. That's the default. But you can also jump. So first you can keep the filter over this segment or this part of the matrix, and then you can either put it here or you can put it here. Okay, so you can take a step of 1, or you can take a step of 2, or you can take a step of 3. So that is the steps that you're taking in the and y direction, or even in the z direction if it's a 3D convolution. That is known as a stride. So strided convolution is another piece which is used in the convolution CNNs. We call the stride S, and when we are making the convolution operation, we use S to tell the number of pixels we'll jump when we are convolving the filter or kernel. So in the last example we described, so S was 1. Now, the general rule is that if a matrix of size n by n is convolved with a filter of size f by f with a padding p and a stride s, so that will give us a matrix of output size which is n plus 2p minus f plus 1 divided by s. The whole thing would be okay. So sorry, the plus 1 will be outside. So this s would be divided by n plus 2p minus f divided by s plus 1. And so if this is a fraction value, so we can take the floor of this. So basically what this means is that if you are having a stride of 2, okay, so if you are having a stride of 2, and in this case your matrix was 6 by 6, so first it will be here, then it will be So then it takes a step of 2. So then it will be here, and then you see here. I mean, we get one extra column. So in that case, you basically take the floor of that float number, and so in math textbooks, they say that the conversion is flipping the filter before using it. What we were doing is the cross correlation operation, but the state of the art deep learning is using the this as the convolution operator. And some same convolution is a convolution with a padding. Uh, so basically same. We will use the same keyword while doing convolution. So you must have seen, if you remember in the hands-on sessions, we have seen that while defining the convolution con 2D, if we give padding equal to same, so that basically means the size of the input and the size of the output remains the same. Now convolution over volumes. So we have seen how convolution works with 2D images. So we can also see how it, if we want to convolve over 3D images, which in computer vision corresponds to red, green, and blue (RGB), and we will convolve an image of height, width, number of channels, and a filter of height, width, and the same number of channels. So the dimension, so the third dimension is taken as the number of channels. So here we are saying that we have a series of 2D images stacked together. So the first image is corresponding to red, the second image is corresponding to green, and the third image is corresponding to blue. So these we consider as the number of channels, and we what we also do is we have a filter of size, height by weight by the same number of channels that you are considering for the input image or the input 3D volume. So the hint is that the image number channels and the filter number of channels are same, and we can call this as stacked filter for each channel. So for example, the input image is 6 by 6 by 3. So this 3 is the number of filters in this. The size of image is 6 by 6. Our filter size in this case is becomes 3 by 3 by 3, and so the resulting image that comes out, so that we want from this is, so 6 minus 3 plus 1, 6 minus 3 plus 1, which is, so 6 minus 3 plus 1 is 4, 6 minus 3 plus 1 is 4. Okay, just a minute. Yeah, sorry for that interruption. I am audible, right? There is no issue with the audio.
Yes, sir.
Yes.
Yes, sir.
Okay, okay, thank you. So we can. So the thing is, we can see that, so 3 is the dimension in the input image, and then 3 is also the filter size. So 3 by 3 by, so this becomes, so 3 minus 3 plus 1. So that is, so 3 minus 3 plus 1. So that the output in this case, so the resulting image that they're saying is 4 by 4 by 10. So that is, I think, because, okay, yeah, because we have 10 filters. So that is why the resulting image is 4 by 4 by 10. And okay, so in the last result, the padding was 0 and the stride was 1. So then we also have the concept of one layer of so we can see the a single layer of a convolution neural network. So first we convolve some filters to a given input and then add a bias to each filter output and get the ReLU of that result. So we have seen in the previous classes what ReLU is. So ReLU is rectified linear unit. The this nonlinear activation function corresponds to max of 0 comma x, where the input is x And then for example, if the input image is 6 by 6 by 3 and you use 10 filters of size 3 by 3 by 3, so in that case the resulting image will be 4 by 4 by 10. So basically if you have 10 filters, so the output will be, so you will be applying these filters, these 10 of these filters, so your output will become 4 by 4 by 1, which is equivalent to 4 by 4. So you will have 10 such maps. So then the resulting image becomes 4 by 4 by 10, and you add the bias B with with the number of bias weights are 10. So then we can add this, will we add to this image 4 by 4 by 10. So that is basically W into the linear combination plus B, and then you apply ReLU. So what you will get basically from here is, so ReLU of the weights into the linear combination plus V. And so in this one we have the padding as 0 and stride as 1. So the number of parameters that we have in this case is 3 into 3 into 3. So we have 27, and that corresponds to the weights in one filter, and we have 10 filters and we add 10, so that is the bias. So this becomes 270 plus 10, so we have a total number of weights as 280. So this number is very important. So this is like in linear regression, if you remember, we were talking about y is equal to mx plus c. We just have two weights. Now in this case, in a single layer of a CNN with 10 filters of size 3 by 3 by 3, that has 280 weights. And this example forms a layer in a CNN, and so no matter the size of the input, the number of parameters is same if the filter size is same. So if so the number of parameters that basically depends on the on the size of the filters, and which would lead you to overfitting problem. And we have seen some of the methods to avoid overfitting. For example, regularization, or different types of regularization, L2 regularization, and dropout. So so then here are some notations that are very commonly used when you are building a convolution neural network. So f of L is the filter size. So P of L is the padding, S corresponds to the stride, and N is equal to NC is equal to number of channels or the number of filters. So if you have an input in the L minus 1th layer, which is N by N by NC, or NH by NW by NC, so height by width into the number of channels. And so you want the output which is N by N by NC, which is uh, so for the Lth layer. So this is from L minus 1th layer, you are going to the Lth layer, and where NL, so N is equal to N in the previous layer plus 2 2 times the padding minus the filter size divided by the number of strides plus 1. So, for example, each filter is f by nc. So you see we have kept the number of channels in the filter same as the number of channels in the input. Now the activation then is, so activation A then becomes nh by nw by nc, and so our weights then become f by nc by nc. So that is basically this is corresponding to a single weight, and this is, so nc in the next layer, so number of channels in the next layer corresponds to the number of weights that are applied to the previous layer. So so the total number of weights becomes n f by nc in the layer minus one multiplied with nc in the previous layer. and the bias number of bias terms are 1, so that's basically equal to the number of channels in the next layer. So in a very simplistic convolution neural network, so are these things clear? Because you need to understand how the unit, when you are building a convolution neural network using TensorFlow, or if you're building from scratch, you should take very special care about the shape of the input and outputs, the number of filters, the padding, the strides. So these concepts are very important to understand. Otherwise, it becomes messy to basically build such convolution neural networks. So is this clear with all of you?
Yes, sir.
Okay. So then we would build a simple convolution neural network. We'll see an example. So the input image is 39 by 39 by 3. Okay, so n here is, so the n is the size of the input image, so that is 39. Number of channels is 3. Now in the first layer, we'll see that we are using the size of the filter is 3, the stride is 1, padding is 0, and we are using a total of 10 filters. So when we apply this filter to this image, so then the output becomes, so 39 uh, minus so minus 3, that becomes 36, plus 2p, so plus 0, divided by s, so that is 1, so 36 by 1, and plus 1, so we would have the size of the output is 37, and 37 by 37, so this will become 39 by 39, and so the number of channels is same in the filter, so that will be cross 1, that's a redundant dimension. And you would apply this filter with the kernel size 3 by 3 to this input 39 by 39 by 3 10 times, so you would basically use 10 filters, so that is why we have the output dimension as 10. Now in the second layer, so this now becomes your input. So then you would apply the nonlinear activation to this, but the size will remain the same. So then in your second layer, if you, let's say you use a filter of size 5 by 5, stride is 2, padding is 0, number of filters is 20. So your output will be basically 37 minus 5 is 32, plus 2p, so 2 into 0, so 37 minus 5, 32, divided by the stride, so that is 32 by 2 is 16, and plus 1 is 17, and the number of filters that you use is equal to the last dimension of the output here. So here you can see that shrinking, it goes much faster because the stride is 2. Now in the third layer, so similarly we will apply the filter to this third layer, so 17 by 17 by 20, and we'll use a kernel size of 5 by 5, stride of 2, padding of 0. So we can see that the output number of filters here is 40. So the output here now becomes 7 by 7 by 40. So in this case, in the output, the size of the image that forms becomes 7 by 7. Number of channels is 40. Now the fourth layer is a fully connected layer. So in a fully connected layer, what you would do is you would flatten out this all these. So this is like a 3D cube. So you would flatten out all these numbers, and you would form a fully connected layer, which is having a size. So this is a vector of size 1960. So 7 into 7 into 40, it becomes a vector of size 1950, and so you can apply softmax to this, and we have seen that the image are getting smaller after each layer, and that's how people apply the convolution neural networks. Now there are different types of layers in the CNN. So one is the convolution that we have seen. Then another is known as pooling, and then we have the fully connected layer. So this is the fully connected layer, wherein we would expand the the entire 3D cube into a 1D vector. So then comes the pooling layers. So other than in pooling layers, what you do is the most common type of pooling is max pooling. So for example, you have this input and you are applying max pooling to this. So pooling is basically done to reduce the size of input, speed up the computation, and to make some of the features it detects more robust. So a max pooling example in this case, so this case where the filter size is 2, stride is 2, and padding is 0. So basically first, so you have the filter size 2 by 2, stride is 2. So what you do is you take the max values. Okay. So max of 1, 3, 2, and 9 is 9. Max of 2, 1, 1 is 2. Max of 1, 3, 5, and 6 is 6. Max number of 2, 3, 2, and 1 is 3. So the max pooling is saying if the feature is detected anywhere in this filter, then keep a higher number. The main reason why people are using pooling is because it works well in practice and it reduces computation. And it has no parameters to learn. And examples, you can also apply it on a 3D input. So your size of the channels that would basically remain the same. Average pooling is, so just like max pooling, in average pooling you would typically take the averages of the values instead of taking the max values, and max pooling is used more often than average pooling because it's more common than average pooling in and used as in practice. So okay. So if max pooling is used more than, yeah, if stride of pooling equals the size, so then it will apply the effect of shrinking. So you can see here, this is basically shrinking the output, and the hyperparameters that we have until now in convolution, they are the number of that is the filter size, the stride, the padding, and the max or average pooling. So then here is the another example of a convolution neural network. This is from LeNet that he has shown. So we have the input image here, first convolution layer. So you can see here 28 by 28 by 6, and then you are applying max pooling with filter size 2, stride as 2. So this one basically becomes 14 by 14. Okay. So then again you apply convolution, and then you do the linear combination, you do non-linear activation, and then you do max pooling. So this gives you a size. So 10 by 10 becomes 5 by 5. And then in the third layer, so you are having 5 by 5 by 16. So third third connected layer, uh, yeah, where is this 120 coming from? So okay, yeah. So this this basically is 25 into 16. This is 400. Yeah. So the number of neurons in the, yeah. Okay. So the number of in the third fully connected layer. So if you are going from this one, so you are basically using 120 weights. So the output becomes 120 by 1, and then you are using 84 weights. So the output becomes 84 by 1, and number of neurons is 10 if we need to identify the example for the 10 digit. So if you want to do, for example, the MNIST problem, and so you can see that you can build this kind of a table wherein you can see that the layer, the type of the layer in the first column, the activation shape in the second column, activation size in the third column, and the number of parameters in the fourth column. So the hyperparameters are, there are a lot of hyperparameters, and to choose the value of each, you should follow the guidelines that they would discuss in like later. And so the usually the input size decreases over the layers while the number of filters increases. That's a standard practice, and a CNN usually consists of one or more convolution, not just as shown in the examples, followed by a pooling. So, and a fully connected layer has most parameters in the network. So to understand these blocks, you should look at other working examples to get the intuition. So why convolution? Two main advantages. You share parameters. So you have a feature detector wherein you don't basically build handcrafted features, and you have sparsity of connections. So in each layer, each output value depends only on a small number of inputs. So for example, you have a training set. You have an input image X, and you have an output Y. So whether this is a cat or not. So you have a convolution layer. A convolution layer, I think they might also be having max pooling, and then you have a fully connected layer. So two fully connected layers and one output. So you basically compute the cost function divided by the total number of samples. So that is or multiplied with 1 by m, and and you compute the sum of the loss between the y hat, which is the y predicted, and the ground truth. So we'll see some case studies, using some classical uh, CNN networks. So the first is LeNet, then we have Alexnet, and then we have the VGG net. So the best CNN architecture that has won the image, so just like Mnet. So there was a competition. I don't know if it's still running. It was called as the ImageNet competition, wherein you would be given a task of classifying these digits, or doing some different other types of classification, and you would have to come up with a model which does the best performance, or which gives the best accuracy over the task. So the model which was giving good result was ResNet, and then another architecture came which was known as InceptionNet. And so reading and trying the mentioned models can boost you and give you a lot of ideas to solve your task. So in the classical network, so we have the first one is LeNet. So the goal of this model was to identify handwritten digits. You have a input image of size 32 by 32 by 1. You have a filter of size 5 by 5. Stride is equal to 1. So 32 minus 5 is 27, and they don't give padding here. So padding, I think, is 0, and you divide it by 1. So 27 by 1 plus 1 gives you 28. So you basically use 6 such filters of 5 by 5. So this you have this 3D matrix of size 28 by 28 by 6, and then you do average pooling. So you do average pooling with filter size 2, stride as 2. So the size of your matrix, it reduces, becomes 14 by 14, and then you do another convolution and another average pooling, and then you open this up. So you have a fully connected layer, but the number of weights here between this layer and so in this layer in between is equal to 120. So that is the reason we have 120 neurons here, and in this layer in between these two layers, the number of weights we have is 84. So that's the reason we have we have no, not the number of weights. So we keep the size of this as 120, and the size of this number of nodes in this fully connected layer as 84. Now this model was published in 1998, and so the last layer, they say, was not even using softmax. It had 60,000 parameters, and the dimension of the image decreases as the number of channels increase. So you can see convolution to pooling to convolution to pooling to fully connected softmax. And this type of arrangement is quite common. And this activation function used in this paper was sigmoid and tanh, and modern implementations they use ReLU. Now the next model was known as Alexnet. So this was named after Alex Krzyzewski, who was the first author of this paper. The other authors include Geoffrey Hinton. So also you should know Geoffrey Hinton is also known as the father of deep learning. So, or yeah, Google says father of AI. And Geoffrey Hinton and Joshua Bengio and Jan LeCun, on whose model is LeNet. These were the three people who pioneered the deep learning field or ecosystem. Like they are leaders in AI today, and they have been driving the success in deep learning and artificial intelligence. So yeah, recently they also won this Turing Award, which is named after Alan Turing. So the goal of this model, so this is Alexnet model. So also was on this was on ImageNet challenge. So ImageNet challenge has 1,000 classes. So in this challenge, you are given an image of size. You are given an image of size 227 by 227 by 3. The first filter you use is of size 11 by kernel size 11 by 11, and the stride is 4. So 227 minus 11, that becomes 216. You don't have padding, so plus 2p is 0. Divided by 4, so 216 by 4 is 4 5 is 20, and 4 4 is 16, so 54 plus 1 is 55. So then you would do max pooling. So 55, then you see 55 by 2, it becomes 27.5, but we are taking the floor, we are doing a floor of this. So then this becomes 27 by 27 by 96. And then you would do you would basically do a convolution with the padding as same, and you would use 256 filters of size of kernel size 5 by 5. Now you would use a max pooling with the kernel size 3 by 3 and stride as 2. So basically your 227 by 27, you will, so one side is 27. So you basically take us you choose three elements, let's say for a particular dimension, and you take steps of 2. So then the output becomes 13 by 13 by 256. So then you do convolution, and again you do convolution with the, what is this not mentioned. And then what you would do is you would have these three fully connected layers, and in the end will be a softmax layer, which is the output, which will be having 1,000 classes. So this was similar to LeanNet but much bigger. It has 60 million parameters compared to 60,000 parameters of LeanNet. It uses ReLU activation function, and the original paper contains multiple GPUs and local response normalization. So multiple GPUs were used because the GPUs were not so fast at that time. This was in 2012, and researchers proved that, okay, so yeah, I mean they use some method known as uh, local response normalization. Okay, so for now, don't bother yourself on this. Yeah. So this paper convinced the computer vision researchers that deep learning is very important. Now the next model that became popular was a modification of Alexnet. It is also known as the Btg model. Comes in two versions, Btg 16 and Btg 19. Btg 16 consists of 16 layers. Btg 19 consists of 19 layers. So instead of a lot of hyperparameters, we will be having a simpler network. So in this, you have image of size 224 by 224 by 3. So your task is on ImageNet. So you have 1,000 classes. Would do a convolution with padding same. So number of filters is 64. So this becomes 224 by 224 by 64. Do pooling with so this the size, you do max pooling here. The size reduces, and then you do another convolution keeping the padding same, another pooling, another convolution, another pooling, convolution pooling, convolution pooling. So you bring the size from 224 down to 7 by 7 by 512. So this 512 is the number of filters that might be used in the previous layer, and then the number of neurons in these two fully connected layers is 4096 and 4096. And this network is large even by modern standards, consists of around 138 million parameters. Most of the parameters are in fully connected layers. It has a total memory of 96 MB per image for only forward propagation, and most memory are in the early layer. So the number of filters increases from 64 to 128 to 256 to 512, and 512 was made twice. So pooling was the only one who is responsible for shrinking the dimensions. There is another version BG16, BGG19, which is a much bigger version, but people use BG16 instead of BGG19 because it does the same. Maybe it's showing the same kind of accuracy. And VGG paper is attractive as it tries to make some rules regarding using CNN. So this paper came out in 2015. Now, then after this, the networks that gave that even surpassed the accuracy of VGG were known as residual networks or ResNets. These are very deep, very deep neural networks which are difficult. So they talk about like if you keep on increasing the number of layers, it's difficult to train because of vanishing and exploding gradients problem. And what you would typically do is use something known as skip connection. So rather than just going, so you would basically go in a sequential manner. So you will have this layer, a linear combination of weights, non-linear activation, linear combination, non-linear activation. But you would also just directly do a shortcut or a skip connection from this layer to this layer. So that is a skip connection or a residual block, and the authors of this blog find that you can train a deeper neural network using stacking this block. So you can see that now we are having this residual block. So we are stacking these residual blocks, and these residual networks are neural networks that are consist of some residual blocks. So these networks can go deeper without hurting the performance. In a normal neural network or plain network, the theory tells us that if we go deeper, we will get a better solution to a problem. But because of the vanishing and exploding gradient problem, the performance of the network suffers as it goes deeper. So thanks to the residual network, we can go deeper as we want now. So you can see that on the is the so green is what should have what we expect in theory. Blue is what you get in reality, or for example, maybe for the validation set. Or yeah, this is shown for the training data. But in the ResNet, if you increase the number of layers, you would basically go down on the errors. So yeah, in some cases, going deeper won't affect the performance, and that depends on the problem on your hand. So people are now trying to train 1,000 layer neural network, which was not the case before. So why ResNets work? So we need to see some examples why these models are working. So if we have a big neural network like this, so X and a big neural network, and then this A as the output. So we add 2 layers. Let's add 2 layers to this network as a residual block. So we add, so we say X to big neural network to A, which is the activation function, to layer 1 to layer 2, and then AL plus 2. And A has a direct connection to L plus 2. So A also has a direct connection to L plus 2. And suppose that we are using ReLU activation, and we are using L2 regularization. So for example, WL plus 2 will be 0. So yeah, I think yeah, this is too much of detail which you can see later. And so these are the architectures of these models. So VGG19 looks like this. Then we have the VGG. So we have a 34-layer plain deep neural network, so which is the second in the second row, and then we have a 34-layer residual network. So you can see we have these skip connections. Yeah, so then you can see this tutorial on uh, deep residual deep residual networks. No, So I think, yeah, this is actually too long code, and you can see again. Yeah. Okay. So that was all about today's class.